Okay, so in the previous video, we talked about windows and ranges, right? So these windows and ranges are very important because it gives me wiggle room where these functional groups can show up because that's my real job of infrared. My job is to analyze a compound and for me to tell you what functional groups are present and what functional groups are not present. So we said that each functional group has a window or wiggle room to give me a positive signal. All right, so this is eventually what we're leading up to. And this is what we call a spectrum, an infrared spectrum. Okay, we saw spectrums when we analyzed compounds on UV vis. The difference is that this spectrum looks a little different, right? Instead of the humps pointed up, these humps are pointed down. So in the beginning, I see a flat line, and then we see a hump that happens or a dip, and then it comes back up. And then another dip happens and it comes back up. And then another dip happens and it comes back up. So this is what we call the spectrum. And these are what we call shifts or spikes or absorption bands. We are absorbing light. Okay? Something to look for on the graph. Down here at the very bottom, you see that the number 4,000 starts over here to the left. And then if you track it across right-handed, you see that this starts at 6 or this ends at 600. A lot of times people think that this is backward, but it's not. It's 4,000 per centimeters to 600 per centimeters. All right, so what do I really mean by that? Well, we'll eventually talk about it, but on the x-axis is wave number. And wave number is provided in per centimeters. So it starts at 4,000 and it ends at 600. This is the traditional axis that we find in infrared. But this is 4,000 per centimeters and 600 per centimeters. All right, so this -1 basically means kind of inverse. So what that means is that if I take a calculator and I do 1 over 4,000, I see 0.00025. And then if I take 1 divided by 600, I see 0.0016. Now, this is something that you're accustomed to because this is a really small number over here to the left, and this is a larger number over here to the right. Okay, so at first glance, it looks like the x-axis goes backward. It looks like they're starting with a bigger number and it's getting smaller. And some people are very confused. Why does it go backward? It doesn't go backward. The problem is the units that we have to measure in, and these units are per centimeters, which means that we take the number like 0.00025 and we take the inverse of it to get 1,000 or 4,000. This, to some people, is a better number to look at than these really tiny fraction numbers or tiny decimal numbers. The same thing happens here. 600 per centimeters or 600 wave numbers is actually 0.0016 centimeter. Well, this is a bigger number than that one, but when you do the inverse of it, it turns out to be a smaller number in terms of wave numbers go. All right, so I know it's kind of confusing, but the take-home message is trust me, I know what I'm doing. All right, and trust yourself, you know what you're doing too. So 4,000 starts to the left, 600 is the right. Keep in mind that's increasing. not decreasing because of the unit. Something else that you need to look at is the y-axis. So this is percent transmittance. So we've seen percent transmittance before. Percent transmittance is basically how much light is getting through. So in the beginning, maybe all of the light is coming through the sample. It's not absorbing at all. So that is 100% transmittance. All of the light goes through, nothing gets absorbed. And then there's going to be a workout day that the molecule's interested in. And it goes to the gym, and it begins to stretch, and it begins to bend. When that happens, the transmittance plummets and it goes down. And that's because the molecule is now absorbing the light. Not enough light is going through as it did before. And then as the infrared spectrometer scans through the wave numbers, it comes back up because now the molecule's not interested in those workout days, and it goes back to 100% transmittance. Then we might see another spike. The molecule liked it that day, and it comes back up. And then another spike, and then it comes back up. And then maybe a couple of spikes that happen here, back and back to back, and that's what we call our infrared spectrum. Okay? So percent transmittance on the y-axis and wave numbers on the x-axis. And wave number is basically 1 divided by the centimeters. Centimeters is used because nanometer is too big. Remember, we're looking at 100,000 here or lower. Some people don't like to write that many zeros. So they take the nanometer and they convert it to a centimeter. And then for some people, they still don't like that number. And then they say, well, we're going to take 1 divided the centimeter, and that's what we call centimeter to the minus 1, or per centimeters. That unit is called the wave number, and the wave number has an abbreviation, and it's basically a cricket-looking V. That is the wave number that we will associate with infrared spectroscopy. All right? So in this spectrum, what you will eventually find out is that if the molecule has a C double bond O present, you will see an absorption that happens at 1700 per centimeters. Now, here's the wave number, and I forgot to put my little squiggly on top, right? So these typically do have the little squigglies on top of the V, but I just didn't write it. So at 1700 wave numbers, which is about right here if I look at my x-axis, I see a big dip that happens in the spectrum, and then it comes back up. If the molecule has a C double bond O, that is the shape that I will traditionally see and the area that I will see it in as showing up as being present. Well, if the molecule has an OH group, an alcohol, this will happen around 3400 wave numbers. So at 3400, right here on the x-axis, I come up and I see a huge big dip, right? The molecule is absorbing light because it likes that workout day. And then it goes back up. That is symbolic of an OH group, an alcohol group. So, the job for me in infrared is to look at these dips in the spectrum and for me to walk away saying, by looking at these squiggly lines, well, your molecule has an OH group. Well, your molecule has a C double bond O group. Well, your molecule has this type of group. That is what we're after. That is what we want to see. That's what we want to accomplish. So I'm going to have to become familiar with the functional groups, and then I'm going to have to become familiar with the areas that it does absorb light energy from, and where that is located each and every time. Right? Now, our job here is not to figure out what each one of these represents. That's way too much information. No one really can do that, and even if somebody's been in infrared spectroscopy for years, no one probably could tell you what every single band represents. But I should be able to pick up the big ones. That's a big dominant one. I see that immediately just by looking at it. I should be able to tell what that one is. This one, that's a big band. I should be able to tell you what that represents. This one, that's another very dominant band that my eyes immediately go to when I see the spectrum. I should be able to tell you where that's coming from. There's a part of the spectrum, though, that I really don't concern myself with. There is a point here where too much becomes too much. And this is the right-hand side, about the third of the right-hand side of the spectrum. This is what we call the fingerprint region. And the fingerprint region is an area that is very specific to each molecule. And there's just too much going on in there. So I never really take a look at the fingerprint region and try to pinpoint what each one of those spikes are leading to, or what each one of those represents as far as functional groups go. The fingerprint region happens in a specific area, and that is 1400 to 600 wavelengths, or wave numbers, sorry. That is my fingerprint region. So in this infrared, anything after 1400, which basically starts right here, there's all of these spikes that come down and come back up and come down and come back up. I never really bother with those because those are too specific. I can't provide you a general statement on what absorbs where in the fingerprint region. These are very specific to each and every molecule. Now, there's a few that we can talk about, but not very many. And we will talk about a few of those. But for the most part, 1400 and on down to 6, we kind of ignore. And we don't really have to pay attention to those at all and talk about functional groups there. Which means that if I stop this at 1400, I should be able to tell you where this band is coming from, and I should be able to tell you where this one's coming from, and I should be able to tell you where this one's coming from. And that is our main goal throughout the upcoming videos. And we'll start with one functional group at a time. So fingerprint region, we're not going to go there. There's too much. And there's no way that we can generalize anything to make learning it very easy. This is something that just comes with you running samples and getting comfortable with the spectrum and how that particular molecule behaves. Okay? So, keep them coming. That's what I'm going to tell you. Keep the videos coming, keep the play button pressed, and keep watching them one after another.